Hi everyone. Today we're going to talk about the Mirasol display from Qualcomm, focusing on how it works and how it's made. The market is dominated by LCD screens, and its main competitor are OLEDs. There's one notable exception in e-book readers, with e-ink displays being featured in several devices. Several arguments can be made against LCDs for reading. One is the direct light entering your eyes. Another is the dependence on environment. In a closed room with the lights on, we have 80 to 100 lux, or 80 to 100 lumens reflected from every square meter of surface. That's not too bad. Our screens can produce enough light to overcome this. In sunlight though, we have orders of magnitude more light, and LCDs and OLEDs look washed out. E-ink though, and Mirasol displays work fine. Mirasol is interesting because it can do more than emulate monochrome paper. It is capable of color and video frame rates with very low power usage. So, how does the Mirasol do all these things? Imagine we only want the green pixel active. When indoors, some of the room light is reflected off the screen. We turn on green, turn off red and blue, or block light from reaching them. The unintended light that gets through, plus the reflected light, is the black level or darkest pixel. This must be much lower than light from the green pixel. What we need is contrast. Indoors, the contrast is fine, but in sunlight, much more light is reflected. Our pupils dilate and we have a hard time distinguishing pixels that are on from pixels that are off. We have to use the maximum power output for contrast, and it's still lacking. In contrast, the Mirasol display does not have to compete with the sun. Let's turn off the backlight and save all that power. Instead, let's control the color of the pixel directly, which keeps the contrast constant along cross lighting intensities. So Qualcomm published this chart comparing the Mirasol to thin film transistor LCD displays to demonstrate their contrast capability. A score of 32 just noticeable differences means that the brightest pixel is only 32 times more intense than the smallest change our eyes can detect. Here you can see the contrast improvements from the Mirasol display over traditional LCD displays. Now, the Mirasol is an interferometric modulation display, and its trick to controlling the color of a pixel is in the name. Each pixel is made of two mirrors that both reflect and transmit light. At each pass through the gap, some light is lost, and we have a continuous series of light beams with decreasing intensity. The key is that all of the beams of light entering your eye interfere. Intensity is lost at each pass, but there is also some phase added by the extra distance each beam of light travels. You have to add all the beams with their phase shifts to get the output beam. The light out depends on the wavelength of light, red the longest, blue the shortest, and also the phase offset added to each beam, which is the distance between the mirrors. For a pixel, we only need to worry about the reflectivity in the visible range. The lights on the display are made of several wavelengths, and its spectrum can have varied shapes. The pixels we just described act like filters, where only certain wavelengths or colors are reflected. Example, blue. Different cavity lengths make different filters, which give different colors. Collapsing the pixel makes sure that there are no reflectivity peaks in the visible range, and we get black, very low intensity broadband light. To control the mirror spacing, we apply a voltage. This brings charges to the conducting surfaces, which in turn creates an attractive force between the two charged plates. This force has to overcome the mechanical restoring force of the membrane. So, we increase the voltage to increase the electrostatic force to collapse the membrane. These forces change with the mirror's position. The mechanical force increases linearly, and the capacitance exponentially, which increases the charge stored similarly. This further increases the electrical force, which means we no longer need a high voltage to maintain the closed pixel. This, in turn, saves power. The switching is fast enough for modern tablets and low power enough to compete with e-ink. So, in summary, a Mirasol pixel consists of subpixels with mirror separation set to reflect red, green, or blue. All we do is collapse a pixel when we want it to display black, and in low light, the display is lit by front-side LEDs. This all translates into impressive power performance. Qualcomm published data comparing the Mirasol to LCDs in cell phone usage. It showed that Mirasol has very low power requirements and could potentially make a big impact in cell phone battery life. Additionally, Qualcomm was able to create enough displays for the first commercial ebook reader to feature the Mirasol screen, the Kyobo e-reader. It's available only in Korea, and its specifications and name market it as an e-reader, not a tablet, though its price makes it a hard sell. Currently though, this is the only device where you can get 2 weeks of battery life and a color screen capable of video. So, how do we actually make it? Manufacturing starts with a standard glass substrate. We then deposit and pattern chrome molybdenum for interconnecting electrodes. Now, chrome molybdenum, along with many other materials Qualcomm used, is common in LCD fabrication, which in turn reduces the cost. So we now insulate the wires, deposit and pattern the fixed mirror stack, protect and insulate this layer as well, deposit molybdenum as a sacrificial layer to support the flexible mirror, etch a via to the interconnect, deposit and etch the supports for the flexible layer, deposit and etch the flexible mirror including etch holes which will in turn expose the sacrificial layer, and then we release the pixels by removing the sacrificial material in a dry etchant, xenon difluoride. The array of pixels are then encapsulated to protect the moving parts from moisture. A desiccant is also added to further prevent damage due to moisture. Lastly, whatever additional modules the screen needs are added to the substrate. These SEM cross-sections, taken by System Plus Consulting, show how the Mirasol display in the Kyobo e-reader was put together. They also show some close-up SEMs of the pixels and the overall pixel layout. Now, there are unique challenges to Mirasol displays. Moving mirrors invite stiction, which is a combination of sticking and friction. It occurs when two surfaces come into contact. Surface tension can keep the mirrors permanently connected, as there is no voltage we can apply to pull the mirrors apart. This is mitigated by using super hydrophobic self-assembled monolayer coatings, dry releasing in xenon difluoride, and desiccants in the package. These mirrors can also have surface effects, which scatter light and add variability to the pixel's response. Secondly, the Mirasol's color gamut is not as broad as in OLEDs or even LCDs. This could be mitigated by tuning each pixel's color's optical stack for high reflectivity of that color. This requires additional fabrication steps. And this doesn't help the viewing angle, though, which underperforms LCDs, likely due to the reflected light's dependence on the optical path length, which is a strong function of viewing angle. Lastly, as a new technology, we know that the cost of manufacture is higher than its traditional competitors. So, how did Mirasol come to be? It was invented by Mark W. Wiles in 1998. Qualcomm then took over the development when they acquired his company, Iridium, in 2004. In 2011, Qualcomm invested $1 billion in a large production facility in Taiwan. The Kyobo e-reader, which uses a Mirasol display, was released that same year. Qualcomm also acquired Pictronics, a company that pursued a different type of low-power color display at the end of 2011. Recently, Qualcomm announced that it will no longer manufacture Mirasol in-house, but will instead license the technology. So, what happens next? It doesn't look too good. The Mirasol definitely attacks some of the major issues with modern displays, but it still has a long way to go, and backing down from their $1 billion investment implies that Qualcomm doesn't think they can get it there. Still, they have gotten a lot further than many would have expected. Perhaps another company will have the tools required to get the Mirasol the rest of the way. Process flows and capabilities were sourced from the following publications. This video tutorial was a final project for Stanford's Nanomanufacturing course. Thanks for watching.